So hello everyone, I'm Sergio Sánchez. I'm a PhD student working on quantum simulation using tensor networks on HPC at the Barcelona Supercomputing Center.
And I'm Mosè Giordano. I'm a research software engineer at UCL.
And we're going to present Extrae. That's a well-known HPC profiler in the HPC community, and we did the bindings to use it with Julia because it had some quirks. So this started more or less last year when I gave my presentation, and at the time I was working in Summer Cluster, and Mosè was working too. He was working with the Fugaku supercomputer, and Fugaku has some quirks that, like for example, like input-output is super slow, but numerical computing is super fast, and we wanted to optimize these things. Other profilers were having some kind of problems because it's not in ARM or things like that. And Extrae is developed at BSc, and it's a wild beast. It can do a lot of things. It's a little bit difficult to dominate, and it was working. And we tried with Julia, and it was we were having crashes, so we had to do our own bindings for this, and we're going to present them. So the first of all is why you want to use these other profilers, these HPC profilers, that Julia's profiler has its own limitations. Julia profiler is based on periodic callstack sampling, and it can also profile multi-threaded applications. And its integration with the VS Code is amazing. Like you can, it's very useful. When you have to use other profiler, it's much less pretty, let's say. And the one thing that's very nice of Julia's profiler is that it can tell you each of the different functions that you have run, if it has run a lot of garbage collection, of it was dispatched dynamically, so maybe you want to fix some type and stability, things like that. But many times there are parts where you don't know why it goes slow. Like maybe your code is type stable, it doesn't have any allocations and still is going super slow, and you know why. And that's why, because Julia Profiler can only profile Julia in some sense. Like, it cannot profile hardware context, for example, or using other protocols like MPI. Or even if, in the end, we are using some other libraries that are writing in C, and they can do allocations too, and we cannot profile them. I think that nowadays, yes, with some part on the allocator profiler of Julia, but you cannot know like exactly which part of C. So in the end, I mean, Julia community, I think, has developed insane obsession for performance, and in HPC we have that insane obsession. We want more and more performance, and one of the questions that we have is that when we have this kind of, okay, we are having a bottleneck, is that are we really using the full power of the machine, or is that the algorithm doesn't, and we need another algorithmic change? So the first question that we have to answer is that is our code really using, is it really exploiting the architecture of the computer where we are running our applications? And for that, there are other very good profilers like Intel VTune, Liquid, Tau, Scorpy, but and Extrae, of course. We need to. So this is just one more aggregation, one more incremental improvement into the ecosystem. These other profilers have some good things and bad things. For example, if Intel VTune, it's only a thing for Intel architectures, and it's closed source. Liquid is nice, but I think that, for example, hardware counters are not very standard way of using them. Tau, I haven't used it, sorry. And Scorpio, I think, is for MPI only. I don't know. Custom, maybe you can correct me later. I don't know right now. So Extrae, it's a provider and a tracer. It's a tracer and a sampler. Sorry. It's open source. It's developed at BSc. It predates to the 90s, where already before BSc was existing, they needed a profiler for this, and it has been in development since then. So it supports a lot of many programming models like MPI, BitThreads, OpenMP, CUDA, OpenCL, C, Java, Python, and now Julia. And also it supports many platforms like it can provide NVIDIA GPUs, AMD GPUs, I think so, ARM machines, Android. The K computer was, I think, the previous to the Fugaku. It has been tested in Fugaku too. Yeah, like weird architectures. Of course, it's for Linux machines, but I don't know any other supercomputer right nowadays that is not Linux, basically. And the good thing is that the tracer can do a lot of things and Sample too. Like with the tracer, you can add manual instrumentation, so if you like that way. A lot of times, we don't like adding manual instrumentation because you have to modify a huge code. So for that, you usually use LD preload. And you can trace like very use like functions. Like for example, you can trace MPI calls. You can trace the CUDA runtime calls. You can also trace system calls. You can also trace memory allocation and memory freeing. You can also trace input-output. And also, just in case you don't like LD preload, there is a way where you can have this DIN-ins, that is a library for binary data writing on dynamically, so you can actually add instrumentation without actually compiling with instrumentation. That's nice. Currently, it's not supported in our build, but I mean, it can be seen if we can add it. And also there is a statistical sampling, a periodical sampling, just like Julia. But this also allows us for, a part of the callstack sampling, it also allows us for gathering puppy counters. So we can have all these hardware counters and see if we are really using the cache correctly, or maybe we are having some kind of branch misprediction. And also, Extrae is extremely low overhead and has a extremely high resolution that we're gonna show later, and it generates traces for 2 other applications. So Extrae is just like the tracer. It doesn't let you see the traces. It just generates them. Then you need another applications to see them. The one is Parabird. This is the one you are mostly interested in. It's just for checking out the traces. But another one that is very interesting is DMMS. That it's basically a network simulator, so you can run your HPC application on your supercomputer, and then if you load that trace to DMMS, you can see that if you change like the network conditions, if you would have a speed up or not. For example, if you have a very big MPI application, you can check out that, hey, what if my network latency was 0, or if my bandwidth was infinite? Like, would that really accelerate my application? Maybe yes, maybe no. So you can actually check them out. So yeah, we wrote Extrae.jl. It's public. It's already in the general registry, and it's basically the bindings to Extrae API. So you have things like the cursor is there. So in general, it's very easy. You just need to put Extrae.init here and Extrae.finish. Many times you don't even need this if you use MPI, as I will show later. And then you can also add some regions to mark that, hey, this is a user function, so this is where my code is actually running. So that when you see the trace, you can discard all the parts where, hey, this is LLVM compiling things, or this is some kind of overhead by using benchmark tools. So you just know where it is. And fun fact, it's that the, So Extrae binaries are in Yggdrasil. So you have it built for all the MPI and CUDA versions that are available, and all the Linux versions too, and ARM I think too. And it was, as a fun fact, it was the first Yggdrasil recipe to use both CUDA and MPI platform adaptation. So don't worry about if you use any CUDA or MPI like combination, it should work. If there is any bug, yes, please contact me. And it also has some kind of preference system, just like MPI preferences. So you can actually change to use the Extrae built by the system administrators, or use the one by Julia. Actually, I had better results right now with system binaries. We'll have to check that better. And also a very nice thing is that it lets you emit custom events. So if you have, for example, here, I don't know, for example, the float, like the type, you could emit an event to say, hey, I'm using this type. Or maybe, for example, the size of this vector. In those cases, so you can actually correlate other metrics like the cache misses with the size of the vector. Just a quick way of how Extrae works. So Extrae has basically three types of annotations. One are states that they are mostly automatic, a little bit weird, but it's just they tell you, hey, right now it's initializing the application, it's running, it's doing networking, just that. It's automatically annotated. You don't have to worry about that. Then you have events. Events are just values. They are just tuples where you have some code that is a uint32 and you have the value that is a uint64. You can call register in that case. So in the trace, you will see, instead of this numeric code, you will see the string. So you know what are really what you are really seeing in the trace, not just numbers. And the last thing that you can annotate is communication. So you have some. This is also automatic in the MPI programming model, where you can see all the communication between the different ranks. There is some support for doing custom communication. We are trying to get this into distributed, so you could also see how long it's taking communications in distributed. But this requires some other improvements in the ecosystem that I will tell later. And also, Extrae is, like I said, it's a wild beast. So it has some gotchas, okay? So it doesn't always work perfectly. It's not everything so beautiful. The first thing is that Extrae has been very well thought about using LD preload, but this interacts super bad with Julia. So in the case that you're using MPI, just use, you have to put the leap Extrae inside the preload preference here. I think that Mosè also needed to, in some supercomputer, also needed to add some more traces. We want to improve the MPI integration with Extrae for this, like MPI.jl. Also that the XML, it's usually configurable using XML file. You can configure it with environment variables, but it's a little bit limited. And currently we don't have an automatic generator for this. We would like to. Also that the traces are text files. These are nice because you can parse them. The bad thing is that they take huge amount of memory. I know a lot of people who have terabyte big traces in Mare Nostrum. So they are big. And sometimes when you run the application and it finishes Julia, it should run the merger, so it takes all the intermediate files to generate the trace. It doesn't always get triggered, or sometimes it has some fails. So you need to call manually the merger, but this is doable. And with this, we're gonna run some examples. And actually, Mosè was with us 1 week, sorry. So, and I tried to teach him Paraver. It's the viewer for the traces. It's a little bit difficult to use. Extrae is nice, and it's a good thing. It's a bad thing. Is that it's super explicit. So it's a bad thing because it's difficult to start using Paraver, but it's a good thing because it allows you to do a lot of crazy things. So, do you want to try something, or should I start with something?
You start.
Okay. Okay, I will with the XP, for example. Okay, so we got to some traces here for the XP, like this kernel where you do two vector scalar product. It's a scalar product, right? It's just it's a scalar product. Okay, and also some strong and weak scaling on Lules, and also on Okami. That's an A64 FX, so it's a Fujitsu chip cluster. And also, we want some also real application. We have Trixie. So I will start with loading one of the traces. This here, Extrae traces, XP. So here, what we are going to see is that there are we're going to see XP in different, using Julia, using Bliss backend, and using OpenBlast backend. Okay, here, this one. As you see, is The interface is not the best one. It's from the 90s. It's still in development. And the good thing is that, okay, so when you want to see some event, you need to create this new single timeline window. I don't know if you see it. It's a little bit small. I think I can try to Okay, I don't know how to change this, so sorry. If you don't see it, I will try to put some pictures in the documentation. So when you click this, you create a new plot here where you can see the execution of all your of all your application. The plotting goes in one thread, so don't get me to this. This is a state. You double click here, you can see this is running, and there are some parts here. As you can see, we have a huge, and this is input output probably because it's creating the traces. And what we can do is that we can, when you want to actually see an event, you have to go to the semantic. Instead of actually seeing a state, you need to go to an event, and you have different values like, okay, show me the last event that happened, or the previous next event, or just the event type. Like I said, it's very explicit. I'm going to just go for the last event value, and the problem is that now we have all the events happening here, so it's going crazy. So what we can do is we can filter by events, event type. We have to equal one of the event types, and then here we have all the different events that we actually have. And for example, I want to go for the L1 datacast issues. If I click here, then I need to reupload. I need to put it in. Oh, but this is a categorical view, and I want, this is like a numerical view, like a numerical value. So I need to change the paint as, instead of code color, to gradient color. And now it's okay. So as you can see here, green ones are the lowest values, and blue are the high values. So here in this time region, I'm having this little one. It's basically like, for example, here it's 3 million datacast misses in a duration of, this is 10 milliseconds, okay? But here there are a lot of things happening at the same time. So what we would like is to actually filter out all the things that are not our user code. So what we can do is put these user functions. So this is what we call our regions. And we can see here all the different user, like all the different parts. In white, they are the times, moments where we are actually running our application. This is not only white, this is a lot of small codes. As you can see, we can go very, very small. So this one, I think it's around 1 microsecond, and we have a resolution of less than 1 microsecond. So that's nice. So we will do is now derive like view where you take these two kind of events, and you are going to try to filter them by just multiplying, because the user functions are just binary values, 1 or 0. And we are going to call this mask L1 datacast misses, for example. Yes. And if we run this again, and we change the to not null gradient color, then we have it. Oopsie. So we have here all the different data cache misses for our code. As you can see here, so this is like when we grow. So what's happening here is trying 3 different element types. This is float 16, float 32, and float 64. And what we are doing here is increasing the size of the size of the vector. So at some point, you saturated cache, and you have a huge amount of data cache misses. And actually, we can actually check out what's the value of these lengths. So we could actually create the event. Again, I know this is a little bit too verbose. It is. And now I'm going to check the... oh, I think it... here, sorry, the first one. Yeah, vector length. Here again, I have to change this. The good thing is that you can save your events, as Mosè will show. Paint as gradient color. Yeah, here. So you can see here that if we actually expand this, that in this case, we start having problems around here. That's around when we have a size of 63 million elements in a vector, more or less. You can also save maybe the bytes or multiply this. Okay, now I'm going to pass.
Do you have the traces that I sent you?
Yes, here in Okami. Okay. Just load trace. Yeah.
Yeah, no, I wanted to show that you can save the session, which is very useful.
Yes.
Because, yeah, you see that you basically need your window, which is a bit painful the first time that you do, but then you can save the session so you can remember all the settings, like all the views that, that you created. And how do I load it?
Here, oopsie. File load trace.
Pause.
Here, and Extrae trace is here in Okami. You have them here.
Okay, and then the session.
Load the session. Let me see if we can load this. Okay.
And so you can actually load both the configuration, or like once you create your own visualization, like I don't know, the vector length, or the other window was for the cache misses.
We have a problem.
Okay, okay, but the point is, once you create your visualization, you can save the configuration of that window, and also of the entire session, like the entire paraver session, and then hopefully, I don't know, you can reload it afterwards, so that you don't need every time to like recreate the individual windows manually.
Okay.
As you can see, live demo is always super cool.
Sorry.
Right.
On that topic, Mosè, is the session independent of the trace file that I'm loading? And then maybe apply it to different runs?
So the configuration is independent. I'm not sure about.
No, the sessions you need the traces, but what you can do is save your custom filters for the events. Yeah. You can save that into configuration files. Yep. Yeah, you need to.
The password.
Yeah, he ran in another computer. That's why. And again, I think.
So the session was invalid, I guess.
Yeah.
Okay.
Sorry, the session was invalid, but I think you need to now to. Okay, put them here in this. Like it's the grace and the 64FX.
Yeah, I mean.
Traces. Okay, to just copy them here. And let's hope that this works. Okay, let's try it now.
But yeah, definitely the first time that you use Paraver, it takes some time to get the configuration, and it took me like 1 day to learn it. But then when you can save the configuration of the window that you generate, that's much easier for the future, which is what we wanted to show. It's not going very well now, but I can tell you it will work eventually.
I think you need to load them. Sorry, you need to load them manually. Sorry about that. Okay, here.
Especially if you do on the same machine, because we did the mistake of moving from my machine to his machine, and now it's not loading.
Yeah. Okay, and this is the. Okay, super. This is and Grace. The good thing is that you now have the traces and you have the.
It works.
Yeah, the traces work.
And the trace works and the
configuration files.
Yeah. very quickly. Or anyway, there is the hint. Like in hint, we can show at least the
Yeah,
IPC count.
for example.
Yes. So another thing is that there are some pre-built configurations that you can show, and this is, for example, the IPC count, the instructions per cycle count. And you can see, so I think this program was running a matrix multiplication, and we wanted to see how many instructions per cycles there were, and yeah, to see the values here.
Yeah, it's a little small, but if you click in one part of the plot, you
yeah.
see that it's right now
okay,
it's
yeah.
like around 2, like the blue path
yes.
is 2.
Yeah, so this was on A64FX, and we have traces for comparing A64FX and NVIDIA Grace, which are both ARM CPUs using the SV instructions. And yeah, okay, so now we don't have much time to go on with this comparison, but yeah, you can have these plots and put them side by side or on top of each other to compare the IPC count and see how many instructions per cycle you're spending in your operations. Do you want to
Yeah, I wanted
say?
just to finish, because we don't have much time. I wanted to show one execution with MPI, so you can see also. This. Look, for example, this one with. So this is this is a execution of Lules. It's a HPC application coded in Julia, and it's coding out of MPI. This has 64 nodes, and you can see them here. Each color here is a different MPI call. So, for example, these red ones are MPI barrier. This green is MPI init, and here where all the computation is actually happening, you see there is all pink is all reduced, and the other are basically weight. And you can see also, whoopsie, you can also see the communication lines. So here is now a mess, but when you're waiting, you can see that which one is waiting to which here. And also you have some other hints, like, for example, getting the MPI size, MPI profile. So here, for example, if we do this, we can see which MPI calls are the ones that are taking more time. So for this application, it's 72% of the time it's actually doing other things outside of MPI. But afterwards, it's MPI weight that's taking a 10% more or less, and also MPI barrier is taking another 10%. And to finish, I would like to just say that there are a lot of things to do. We are working on, on some integration with trace points. Please, we need help with trace points. It's basically a package that we are trying to get. So we have a standard for instrumentation. So if you want this working more seamlessly with Julia, please help us out. Tomorrow, Julian will be around the hackathon, so you can contact him if you're interested. We also have to test CUDA instrumentation. So CUDA works with Extrae. It's that we couldn't test it with Julia applications. We didn't have time. All the ones that we try, they crash it because of other things, not because of Extrae. And also that we would like to maybe try it with other applications. So thank you all.
Is there any questions?
Thanks, great talk. Obviously, I have lots of questions, but most of them we'll take offline. Let me start with one or two. So first is, you showed Parava for visualization. Can you convert the trace files that Extrae produces to other formats, like open trace format or something? Because that would give you access to more visualization tools. As you said, it's from the 90s, it works, but, I don't know.
I haven't seen it. I like once I found out that maybe someone had some converter. I haven't found it again. The good thing is that it's a text file. It's very easy to parse it, so it should be doable. I'm currently working on that to add a parser to the package.
Sure. Yeah. And second question, then I'll leave it for someone else. You showed the timeline view, like traces, where the timeline is obviously the main focus. What about sampling results, where maybe I don't care about the time resolution, I just want to see, where in my code is most of my time spent? Extrae obviously has that feature, right, sampling. Have you tested that? How do you visualize it? Is it also Parava or some other tool?
You use these kind of things, like these things. So this is, let me show it. Oh, no. Wait. It's a little bit hard to. Basically, this is an histogram. You have to use these kind of things. So you have the x-axis is one of the plots, one of the timelines, and the y-axis is another of the timelines, and you correlate them. And you can also add a third plot, timeline for the color. So you correlate them. It's not the best way. You would like to have some other fancier plots. In those cases, what they do, it's you can take here and save it as a CSV file, so text file, and then you process it manually. And officially, there is something going on to have better plots, but it's not. It's it's very preliminary.
Fair enough.
Any other question? No? I think, thank you.